Okay, so there's something else I wanted to mention, which is that you guys asked me, and I was mentioning to you about the MCBU summer program. So I asked, and I received a confirmation that it actually will take place this summer. The website is not yet updated, but we're working on it. But the website is going to look very similar to the website from last year, which is up now. It's just going to have slightly different problems. Some of the projects will be the same, some projects will be slightly different. But the projects will be on a similar style, basically combining mathematics with biology. It's going to be working for this during the summer. You guys will get paid. And the deadline isn't until April. So you should not worry about the deadline being very soon, because you'll have more time to sign up for it and or to apply. I'm not sure exactly how many people get accepted out of the people that apply, but you can apply by April. Okay. So as I was saying before, it's a very cool program. It's got lots of advantages for you. It's a fun activity to do, and it significantly improves your application if you're applying for grad school next year. I definitely recommend that you think about it. So let me write it down. Note. NCBU is up this summer. Apply by April 2014, and I can send you a link. I'm going to try and remember, but in case I don't remember, Krista, can you send me an email to remind me of this? I want to send you a couple of things, like send you homework problems to do for tomorrow, and send you a link about the MCBU program. Okay. All right. Great. What else? Do you guys have any other questions? So no questions? Okay. So actually, I hope you guys have questions about specific problems today and on Friday, because that's kind of what the review session is about. I want you guys to look up things that you didn't quite understand. Like, we can go through them again. We can talk about them again if you want. I wanted to start the review session with a. Okay, so let's start the review session. So review session. I wanted to start with something that is very useful, but we haven't talked about directly in this class, and that is classification of 2D stability. So there's a cool graph that you can make to determine what type of stability a system has, a two-dimensional system. So suppose that you have a system, let's say y prime equals a times y, where a is equal to the matrix A, B, C, D. So any two-dimensional system, and we're going to give names to the determinant and the trace of such a system. So the determinant is obviously A, C minus BD, and we're going to call this thing delta. Okay? The trace of A is A plus D, and we're going to call this thing tau. All right? Yes, fine. AD minus BC. Yes, you're right. Thanks. Thanks for pointing that out. Okay, good. All right, so now we have this, and when we find the eigenvalues, we compute 0 is equal to the determinant of A minus delta, A minus lambda, D minus lambda, B, C, and that's the same thing as A minus lambda times D minus lambda minus BC. It's the same thing as lambda squared minus a plus d lambda plus a d minus bc. It's the same thing as lambda squared minus tau lambda plus delta. All right. So when we solve for this thing equal to 0, what we get is lambda equals tau over 2 plus or minus tau squared over 4 minus delta. Okay? So, for example, how do you know if there's going to be real eigenvalues or complex eigenvalues? When are you going to get real eigenvalues? Whenever the thing that's inside is what? Is bigger or equal than 0, right? So, so this guy is real if and only if tau squared over 4 minus delta is bigger or equal than 0, right? And this is if and only if tau squared is bigger or equal than 4 delta. Okay, so that's just one part of it. But you can actually draw a whole graph that tells you what the dynamics is going to be depending on the value of tau and of delta. So here it goes. We have tau here, and we have delta here. We're going to draw that parabola over there, the parabola given by tau squared is equal to 4 delta. Okay, it's a parabola, right? All right, let's see what happens when the values of tau and of delta are over here. Okay, then on the one hand side we know that do they satisfy the condition for being real, the eigenvalues being real? No, right? This on the top of this parabola we have complex eigenvalues, right? And on the bottom we have real eigenvalues. So over here we have then complex eigenvalues. On the other hand, what is the real part? Is the real part positive or negative? Right here. So tau is negative, right? Tau is negative, so negative real parts, complex eigenvalues, what do we get?
Stable spiral.
Stable spiral, that's right. So anywhere in this region we have stable spirals. Okay? Now what about over here? We are below this parabola, so we have real eigenvalues, right? On the other hand, tau is still negative. So real eigenvalues that are negative, we get what? It's a stable node, right? Okay, and then in the same way you can figure out the rest. For example, what happens over here? Over here we still have complex eigenvalues because we're above the parabola, but we have tau positive, right? So we have now positive real part. So what is that? Unstable spiral, that's right. And over here we have real eigenvalues and positive tau. So if you look at the signs of this thing, you're going to see it's an unstable node. Okay, what about over here? When delta is negative. So let's say that delta is negative. Okay, so this guy here is positive, right? Because we're minus something negative. Then we have a positive number in here. So the eigenvalues are for sure real, right? They're not complex. And this number, the square root of that, is clearly bigger than this number here. So when you add it and subtract it, for sure you're going to get one positive and one negative value. That's what? It's a saddle, that's right. And the same thing happens with positive tau. Awesome. And you can look at more, maybe this case right here is also interesting. When you're here, you have tau equal to 0, and let's say delta positive. So you get in that expression over there, you have 0 plus or minus some real minus delta, right? That's a pure imaginary number, right? So what is the corresponding behavior? It's what we call a center, or just a pure oscillations like this. So there you go. Next time you look at a two-dimensional system, you can, if you remember at least the basic aspects of this graph here, just from looking at the trace and the determinant, you can already figure out what the behavior looks like, which is pretty neat. We were implicitly using parts of this graph a lot of times. For example, you can see here that in order for the system to be stable, whether a spiral or a node, you need to be in this quadrant over here. Anything outside of this quadrant is unstable. You see this blows up, blows up, blows up, blows up. It's only here that you have stability. That's where the tau is negative and delta is positive. Okay. Another thing we used, I think, last time was that as long as delta and tau were positive, you have unstable behavior. When we were talking about repellence, you know, in the Poincare-Bendixson theorem, you talk about steady states that are repelling. Well, these are the repelling steady states, the ones that push away all the solutions, unstable spirals and unstable nodes. That happens if and only if both the trace and the determinant are positive. So there you go. That's, you know. All right, great. So at this point, I'd like to open up the floor to you guys. Do you have any questions, specific problems, or I mean, we can also talk about different topics that we have talked about in this class. Yes.
Can we do some examples on limit cycles?
Sorry, on limit cycles?
Yeah. Because finding
Okay, let's think about limit cycles. That's a good. Or how about in general, periodic oscillations? What techniques do we know to figure out if a system has periodic oscillations? What do you think? How do we know if a system has periodic oscillations? Well, Hopf bifurcations, that's right. Okay, so Hopf bifurcations are a technique where you can study a dynamical system that has a parameter. Okay, we didn't talk too much about systems with parameters, but as the parameter varies, you linearize around the steady state and you'd see some kind of behavior for the eigenvalues. I'm not going to talk right now about too much about the details, but bottom line is you can verify that the system has periodic solutions for some values of the parameter. Okay? Can verify or can prove periodic solutions for some values of the parameter. Do you guys remember there were two types of such bifurcations? What was that again? There was supercritical and subcritical. Okay, I know it sounds technical, but the two of them are actually quite different. One of them proves the existence of limit cycles, which is what Abdon was asking. So in the case of supercritical Hopf bifurcations, we actually have limit cycles. In the case of subcritical, we can only prove the existence of periodic oscillations, but they're still there. Great. By the way, what's a limit cycle? How is a limit cycle different from a periodic solution? Brian, either one.
Isn't it like can be perpetrated by disturbance?
Exactly. So it can be perturbed or it cannot. It cannot, right? So a limit cycle is a periodic solution with the additional property that if you perturb it, if you, let's say you start over here, you converge back towards the periodic solution. You kind of spiral in. And if you start over here, you kind of spiral out. Okay? That's a limit cycle. And there's also another type of periodic solution, which is, so let me write this down. This thing is a limit cycle. It's something like a stable periodic solution. And there's also what we have been informally been calling centers, which is a whole number of rings, like Saturn, right? Where each of those rings consists of its own periodic solution. Okay? Now, an example of a center would be this system right here, where a linear system where the eigenvalues are plus or minus I. But you can also have nonlinear systems with a center. In fact, we didn't prove this, but the original predator-prey model, the Lotka-Volterra predator-prey, is one such center. It looks like that, even though it's a nonlinear system. So the solutions are not exactly circles. They're actually more like, I don't know, like pancake-shaped things, weird-looking shapes, but they still go around in a periodic shape, in a periodic form. Okay, great. So that's one way to prove the existence of periodic oscillations. What about another way? Another way to do it. Natalie, what do you think? How can you prove the existence of periodic solutions?
Is it when we set up the region D?
Yes.
And then
How is that called? Starts with a P.
oh, the Poincare Bendixson.
Yes, Poincare Bendixson. Poincare Bendixson. Theorem, which guarantees the existence of periodic oscillations under certain conditions. Can anybody tell me in broad terms what the Poincare-Bendixson theorem says? Either the general statement or the more applied theorem to prove such things?
Does it have to do with steady states?
It has to do with steady states, yes? Come on, guys, you're just 5 days away from the final. What is it?
Bounded with repelling steady states inside.
Okay, so, Poincare-Bendixson theorem. There's multiple ways to state this result, and there's different variations of it. But suppose that you have a bounded set D. Okay, here's your bounded set D. And suppose that, what about the steady states?
It's repelling.
All steady states are repelling. Then what? Okay.
And any solution that starts in D will remain. Oh, you
Mhm.
also need the
What happens in D stays in D. All right, so then what?
Then any solution in it is a periodic solution or approaches a periodic solution.
Exactly, that's what the Poincare-Bendixson theorem says. In particular, there has to be a periodic solution, right? So it's something like you start here. There may be some steady state, but it's repelling. It doesn't really, solutions must stay away from that steady state because that steady state is repelling. So you take an initial condition and you start running this around. You start running the solution. Well, the solution has really nowhere to go. It cannot get out of D, right? Because solutions that stay in D, that start in D, stay in D. But it can also not converge towards this guy. So there's really only so much that can happen. It cannot even cross itself, right? Solutions cannot cross their own path. So the only thing this thing can do is converge towards a periodic solution. So let me draw it here. There's going to be some periodic solution, which, by the way, now that we know topology, we can guarantee that that periodic solution is going to encompass this repelling steady state, right? Right? And the solution of this system must converge towards that periodic solution there. So you will never actually see this situation. You will never see a set here, the only steady state here, repelling or whatever, and the periodic solution over here. Can anybody remind me why we cannot see this behavior? Because of index theory. More specifically, why? What do you think, Daniel?
What was the question?
Why is this situation impossible? The situation where you have the set D, the steady state, the only steady state is repelling, and you have a periodic solution, but the periodic solution does not include the steady state. It's somewhere else. What does that violate? It violates index theory, but specifically in what sense? Okay, well, you can calculate the index of this path right here, which happens to be the periodic solution. In the index of this thing, we know it's equal to 1, right? Because you go around it once. But on the other hand, we know that it's the sum of the indices of what's inside them. And if we say that the only index is here, then that sum will be 0. Right? So, whereas in this situation, the index is 1, and we know the index of this guy over here is also 1, so the theorem works. No problem. Great. All right, so that's what the Poincare-Bendixson theorem says. The Hopf bifurcation theorem is analytically, it can be a little bit hard to deal with, especially the last condition is hard to check. So it might be a little bit hard to give you an example for the exam, like an actual system. I guess I could give you a cooked up one that is very simple, but only like in polar coordinates. But this guy here is much more general. I can write a set of differential equations and ask you to find a set D that satisfies these conditions. Okay? There's a variation of this theorem that instead of a bounded set D asks for a bounded like torus, like a donut-shaped set that doesn't have any steady states inside it. Basically, that's the same as taking this guy here and cutting it out. You make a little circle and cut it out. Don't include that in the set D. So D now has some kind of annular shape and does not have any steady states. But it boils down to the same kind of thing. Bounded set, solutions that start in D stay in D, and whatever steady states there might be in the set are repelling, whether there is any or not. Okay, so this is maybe a more compact way to write it. All right. Great. What else have we been up to in the last few lectures? What else have we proved? We talked about chemical reactions, right? Do you guys want to review chemical reactions, or do you want to review something else? Yes.
In relation to this, can we do some examples where we find the bounded set D, like we have the same thing?
Yes. Does anybody have the book with them? I seem to have left it. Yeah, you have it? I think it might take me a while to find an example of this. Let me see if there's one. No, sorry, I don't see any. No, basically what the kind of example I have in mind is the following. Suppose that you write the null line of the system, and you find that the null lines look something like this. Okay. Okay, so now this is the y null line or x null line. This guy right here. What null line is it? It's the x null line, right? Okay. And this guy is the y null line. So the idea is everything that's on this point right here has y prime equal to 0. Everything that's below this red curve has y prime bigger than 0, and everything that's above the red curve has y prime less than 0. And you can see that in here, y prime is here is less than 0, y prime is bigger than 0. Okay? So if I looked at a point, say over here, right here, is y prime bigger than 0 or less than 0? Y prime is bigger than 0, right? So it's pointing up. At least the y component is pointing up. You can do the same argument with the x component. The x component is always negative on this side, and it's always positive on this side. So I know that in this case, the y component is positive and the x component is negative, so the vector is pointing this way. Okay. Bottom line, you don't need to think, I mean, that was like the long explanation, but the short explanation is that you take any point that's, say, in between these two null lines, and the direction is a mix of what happens. For example, it points in the mix between this direction and that direction, so it has to point in that way. Okay, but the proof is what I just said. Okay, you can look at the y component because we're below this thing, the y component is positive. Or you can look at the x component because this point is above this black line, the x component has to be negative. So it has to point that way. So all these points point that way. Okay, all these points point down here. All these points point that way. And all these points point, all these vectors are pointing up. Okay, so can anybody think of a set D that might contain, were such that the solutions that start in D stay in D?
Start at the top of the red curve, and then go directly down to the black curve, and directly to the right curve of the black curve.
Exactly. You do more or less like this. Actually, no, not that one. Like this. Well, it doesn't have to be square. Good point.
They didn't know.
Good enough. Okay. So you can see here the vectors are pointing up, and here the vectors are pointing in. Okay. So basically, if you can find the region that works, that sets it all up, then you have your set D. Then all you need to do is you look at the intersection of the two alkynes. That's going to give you the steady states, right? Okay. You still have to show that those alkynes are repelling, that those those steady states are repelling. Now that we've did this, what is an easy way to tell whether it's repelling or not? Which ones are the repelling ones in here? This one and this one, right? Those are the only repelling ones. So you need to check that both the trace and the determinant are positive, exactly. So you take that steady state, you linearize around it, find the trace and the determinant, make sure they're positive. And then you can put all together using that result, and you conclude that there must be periodic solutions. Okay? Yes?
So on a problem, do we just draw it, or do we define the region?
You can just draw it. That's fine. But you need to draw a careful alkyne analysis. Yeah. Yes?
So were we ever able to establish from a picture like this whether that steady state on the right was unstable?
You mean this guy here?
Yeah. It looks unstable.
I think you could. Because you see if the... Well, let me see in this case. Okay, so look, this is all the hallmarks of a saddle actually. You see the two steady states are these two directions are pointing away from here. These two directions are pointing away. So my conjecture is that this is a saddle, that solutions that start here go that way, solutions that start here go that way, and so forth. So you can tell if this guy is stable or not. What you cannot tell is whether this guy is stable or not. Why not? Because this points to an oscillation, right? But you don't know if it's a stable oscillation or if it's an unstable oscillation. So for that, you need to calculate the eigenvalues, or actually look at the linearization itself. Okay? So you can do a fair amount with alkynes, but you cannot do the whole thing. Sometimes you have to look at the additional information. Okay. What else? Yes, Brian.
I have a question about the Lac Criterion.
Okay.
I'm not too sure what it means by does not change sign.
Okay, good question. We we didn't give it that name, but it's actually called the Lac Criterion, and it goes as follows. Suppose that you have a system x prime equals f of xy, and y prime equals g of xy. We have not been too picky about these things in the class, but we're going to assume that this is a C2 system. C2 means that the second partial derivatives, any second partial derivatives you take of these functions are continuous. For example, df dx, and then that with the derivative with respect to y. So for example, df dx dy. Okay, so this, for example, means that d squared f dx dy, d squared g dy squared, etc. are all continuous. Okay, that's what C2 means, and basically it means that these two functions are smooth enough. Okay, suppose that there is a function b from a set D into the reals, where D is a, let's say, a bounded domain. Okay? And suppose that this function is also C2. Okay? So D is a bounded domain and B is also C2. Okay. Now, suppose now the assumption is that the derivative of bf with respect to x plus the derivative with respect to y. Let me write it like this. Suppose that it's always bigger than 0. Okay? If that is true, then the system cannot have the system has not or has no periodic solution in D. Okay. So, but that's not exactly okay. So, what do you think about that statement? Do you understand this statement as it is? If there exists a function b such that this thing is bigger than 0 all over D, then the system cannot have periodic solutions. Does that make sense as a statement? Yes? Okay. Well, the question is how do you find b, right? You know, b is not going to be given. You know, you're given the system, and you're supposed to find b that such that works. Okay? Sometimes it's easy enough to just do b equals to 1. If you write just b equal to 1 all over, then this becomes df dx plus dy plus dg dy is bigger than 0, which is easy, right? It's much easier. That one's called the Bendixson criterion, but I don't want to overwhelm you guys with too many names, so we're not calling it anything, but it's just a special example of that. But it's a criterion to prove the non-existence of periodic solutions. Okay, now there's a tricky part here. My interpretation of it is basically the following. You know, it says, assume that this thing is different from 0 and doesn't change sign. I believe this is the same thing as saying that either this thing is always bigger than 0 or it's always less than 0. Okay? Either it's always bigger than 0 or it's always less than 0. That's how it can be always different from 0 and doesn't change sign. Brian?
Okay, so should there be a problem where you ask us to find b that
There-
satisfies it?
There could be a problem where I ask you to find b that satisfies it, yes.
What if it was like, we can't use 1 of x in this case, right? Or because it's not defined as 0. Right?
Well, but remember that we're not talking about all of R2. We're only talking about a bounded domain. So you could, in principle, talk about b equals 1 over x. As long as you're in a set that doesn't include the origin. Brian, question? No? You were just stunned to hear that I...
Yesterday, and I'm like, well, it's starting to make a little more sense
Yeah?
than reading the book.
Than reading the book?
Yeah.
Okay. Yeah, I think it's a funny way to say it, you know, like it being different from 0 and not being equal to 0. Yeah. Okay. Anyway, so I mean, I'm pretty sure that's what this means. You know, I'm a little bit surprised because if it is less than 0, you can define b to be the negative of, you know, instead of doing that, you'd look at minus b, right? And then that would become positive, right? So the Bendixson criterion in principle could just say if this is bigger than 0, which is much easier to state than different from 0, yada, yada, yada. Can we just do it like that? I mean, look, if you find one function that has b bigger than 0, then for sure it satisfies the criterion, right? So it might be that the criterion is just slightly more general than that, but I doubt it because D is connected. Otherwise, what's the point of showing that there's no periodic solutions? B has to be a connected set. So, you know, I imagine that's what it means. And you know, I may be missing something, but I think that that's really what it means. That it's either positive or negative. Yes?
So you have B bounded in D target?
No, D is a bounded domain. B is not necessarily bounded. But it probably is, sure.
I mean, like your inputs, right? Your x and y's that you choose is going to be, they have to be in a certain domain, right?
Yes.
So when you're using the theorem, would you have to only use those x and y for f and g respectively as well?
Absolutely, that's a really good question. And when I say that this thing is always positive, what I really mean, or what maybe I should say more precisely, is for all points in D, in the set D. Yeah. Okay, and we gave an example of that for the Lotka-Volterra system, where we showed that there exists a particular function B that satisfies this condition. Okay, so so there you go. So basically, Bendixson's strategy to go about this is you're given a system and you ask yourself, do I want to show that this thing has a periodic solution or does not? If my hunch is that it has a periodic solution, then my strategy is to find a bounded set, like this. Sorry. A bounded set with those conditions from the Poincare-Bendixson theorem to prove that there is a solution. If my hunch is that there is no periodic solution, then I try to find a set B that satisfies this. And if my hunch is wrong, then I'm not going to be able to prove anything. It's not that if I go with one hunch, I'll be able to prove one thing, and if I have a different hunch, I'll be able to prove something else. The system is what it is. The system is not going to change depending on my hunch. It's just that if I have the wrong hunch, I'm not going to get anywhere. Okay? All right. More questions? Natalie, what do you think? You good?
Yeah.
What about, well, actually, we're running out of time. But next time we'll talk more about, for example, chemical reaction networks, more examples, Hopf, that kind of thing, if you want. Great. So see you tomorrow, right?